Okay, so as you can imagine, the latest FinFET nodes development cycle become extremely complicated, right? You see all this design constraint and how this process affect the actual property of the devices. So the development cycle become much longer than before. Okay. However, the whole world cannot wait, right? I mean, if you're Apple, you cannot say, oh, okay, yeah, you just do your development and then I'll wait for you for 3 years, then I'm gonna do another product release. There's no way that they can do this, right? So this is the model that people in industry are doing right now, right? So as the foundry, such as TSMC, they are developing their technology, right? So you can see this model uncertainty, right? So in the beginning, completely immature. And then in the past, usually what we do is that we are circuit designer, right? We are in the lower stream. We usually say that, oh yeah, just try harder. Talk to me when you are done. And that's usually in the past maybe a couple months. Okay, when they are have something is more ready, okay, that for the circuit designers that you can do. But now it's taking longer and longer. So what they do now is that they give you this so-called speculative model in the DRC. So the foundry know that you cannot wait. If you are Apple engineers, you cannot wait, right? If you're Google engineer, I don't think you are in any better position. You cannot wait. Okay. So what they're gonna give you is they give you this speculative model. You start working on your design. You still work on your op-amp, I don't know, your ADC, you start working on it. So you're gonna come up with some initial design as they are refining their model, okay? And later on, they're gonna have this updated model, right? They call it silicon influence model. So basically, they will tighten up the uncertainty. Okay, so before, I don't know, maybe it's 2x off, and now it will be like within 1.5x, as an example. So then you go back and then modify your design, right? So you are already designing. You are not wasting your time, right? Right. And later on, of course, the foundry will take out their own chip. So they call silicon based. So they actually measure it. They will go back and do the final pass. Okay. So once they get that, then they will pass that to you, and you finish your final design. So all this right now, they all go concurrently. Okay, so it's no longer by sequential process. After you are done, then I move to the next. So right now it's all have to process everything in parallel. Okay, so this comes to the question where, as I mentioned, even if you have a mature model, right, you model everything, all the LOD, flag everything, but before and after the layout, the result can be quite different. Right? Whatever that you simulate is almost like a joke. All right, so here are some of the wisdom to consider. In the new nodes, you are gonna face more iteration. Okay. In the past, if you are very good analog circuit designers, maybe you say, okay, yeah, just give me 3 times, up to 3 times. I'm gonna write the best design for you. Right now, you need more. Okay. So accept that as a fact. Right. So some of the experience, especially the experienced designer, they have a hard time to swallow this because they pride themselves, right? The entire career, 3 pass, I'm gonna give you the best design. Right now, everything changed. It's not even their fault. It's not his fault. It's not her fault. It's just the way, there's a disconnect between this layout aware model versus non-layout aware. It's just a big difference. Okay. So what are the contributors, right? So earlier I talked about this layout effect, right? So those layout dependent effect, LDE, so layout dependent effect, it change everything, change your threshold voltage, change your mobility, so that's one usual source of errors. Another usual source of error is just parasitics, right? So in the past, you connect the gate, you put a contact, you put a VR, you thought that that's almost like a short. You said, oh yeah, I just short them together. What do you mean? Right now, remember what I just said? You need to consider all those, any connection become a resistor, like you insert a resistor, right? So those are usually explain why there's usually a huge gap. Okay, then what do we do as a designer? We are a designer, right? So one big thing. First, if you can include the source and drain contact resistance. Okay, so sometimes the foundry will have some switch you can turn on, so they will allow you, so they will actually attach this pre-estimated source and drain resistance. So you don't need to add the resistor, right? So right now, if you need to add a resistor in the end cadence, you need to add the resistor symbol, right? Can you imagine you need to do this for every single transistor that throughout your circuits, right? This is way too much work. So I know some PDK, they will actually have a switch, so you turn on, they will include all these resistance, right? So as soon as you actually include source and drain contact resistance, that's already a big help. Big help doesn't mean that it will give you a better performance, no. A big help just means that to get the final performance will be close to what you expect. Okay, so that's one of the big things. And the gate resistance, right, is another big thing, right? So if you can enable that gate resistance estimation to that device model, that's a huge help. Another thing is the CGS CGD, so gate to contact capacitance, right? So if you can enable that, that also can bring in the gap before and after the layout. Okay, so those are the okay. And of course, you should make your schematic more layout aware, right? So you sometimes if you anticipate that I have this long routing or whatever, right? So you can pre-estimate what's your parasitic R, parasitic C's, and if you can just attach that to the schematic. So this is already beyond the device level, right? Even between device to device, if you actually know what is your rough floor planning is, you attach that parasitic R and C, huge help, huge help. Okay. All right. So there is some tips, when you design in this FinFET node. So first of all, because the DLC constraint, right? Try not to mix the short and long channel. Okay. So when you have different long and short channel mixed all together, because of the processing steps, they need to mix all this together in such a close proximity. A, you will make the device less reliable, meaning that you will have more variation, and two, the DRC rule oftentimes they will ask you to space them out. Okay, so you waste more area, right? So one of the common practice, for example, in the current mirror, that's where you want a longer channel length. But then you don't want to mix the one long channel and one short channel. So what do? You see, they do the stack. So the stack transistor is a common practice. So you can all use the short channel as an example, right? And just stack them up. Okay. All right. So that's one of the common trick. Another trick. Remember I talked about this source and drain resistance being too high? Okay, so different circuit has different sensitivity. If in the future you found that, you really get killed by this source and drain resistance, okay, because they are so compact. You can imagine all those contact vias connect to that, it's gonna be very small electrical connections. It's way too small. resistance too high. Okay, so sometimes what people do is that they will discard this device and they take both sides, as if you double your source area. Okay, you double this, so you get more contact here, and you just need to shorten to it. Okay, so that's one way of people use effectively you double that source area, which was not intended, but because you have no choice, you do this way. Sometimes people also increase this source or drain area a little bit more, so that you can pop more contacts right there. Okay, so having this multiple contact is like you have resistor put in parallel. Okay, if you have resistor in parallel, do I increase or reduce the resistance? Reduce. It turns out that this is one of the most popular technique that people do in the feedback. So just whenever you can, just look at your layout and ask yourself, can I pop down more vias? Any way that you can possibly can. Okay, so try that. Okay, so one thing to be careful is that yes, you can reduce the R, but your capacitance will go a little bit higher. Okay, so this is generally true, but in many cases, you are more sensitive to the R rather than C. Okay, C maybe go a little bit, because you see when the R goes up, even your DC get affected. If you go C a little bit larger, it's only affect the higher frequency behavior, right? The lower frequency doesn't change as much.
Can you go back to the current mirror slide? Why would you want a longer lens for current mirror? Wouldn't that have more noise and consume more power?
Oh, that's just RO. You just have a longer, higher L. You have a higher.
But wouldn't
RO.
that be on the load side instead of on the
Not necessarily, right? Because you want to match, right? In the end of the day, you want to match whatever this current to this.
If you tune it
If you have a tunability, yes, you can. But a lot of times you don't have that much of a tunability.
so just match exactly what
You just So some of the cases where you just say, okay, whatever that current 1 microamp here, you want to match, you want to mirror to the other side is 1 microamp. If you do 1-to-1 ratio, maybe you can do 1-to-2 ratio, right? But the point being that there's a certain target value that you try to hit. If you don't hit, if your circuit happen to be able to tolerate that, that's probably okay. But you designed the 536A circuits, right? So you know that, for example, if the bias current, so let's say if this bias your GM cell, it will affect your GM value, right? So the question is that if your GM value changed by this much, what's the overall impact? So that depends on your circuit. Okay, everything will get changed, right? So. Okay. On the metal resistance, we know that, especially on the lower metal layers, right now the metal resistance is very, very high, right? So this one you can see, compared to the source vias, this is like 55 times higher. Okay, so this is on the lower metal layer. But usually when you go to higher metal layers, it will be thicker. But the pitch will be larger. Okay. So this is more and more what people do. In the case where they cannot tolerate this high resistance, you know what? They go up, go to highway, go there, and come down. So in the past, we don't even consider this. We're just like, okay, wait, are you crazy or something? You have just spacing here. You just put the metal 1, metal 2 here, and you are done. And now, no. It's already changed your thinking, because of the construct of all this material, right? All these wires, you just need to change the way how you do your circuits. Okay, so this is what people do, right? So you can see, okay, I stack up, and you're right. If you are thinking that, okay, Mike, that doesn't make sense. If I stack more vias, that's more resistance. And you are absolutely right. Look at this. Your via resistance go up by 3 times. However, your metal routing save even more. So you start to kind of optimize, you gotta go different options, and then maybe this overall you get a better performance. All right. And if you say, hey, I don't want that to be limited by the VIA, so people do this VIA pillar, so they use more VIA. They use array of VIA, so you can see like this, right? It's a bit nasty, but you get to kill the resistance, and that way you get the gain of the lower metal resistance. Yes.
Is it true that using this techniques trade off with the risk of the antenna effects?
Actually, for the antenna effect, you do want to stake up, right? You want to go up and come down. So actually, this will help. Because antenna effect is, when they manufacture this layer, how much charge they would accumulate and then punch them.
Or wouldn't just add a bypass at the connection, like add the power rail, get rid of the antenna effect.
Get a bypass.
Like bypass capacitor, like connecting. So at the power rail, you connect like a capacitor between the power rail and the ground, and then to get rid of the true.
Yeah. No, usually.
Oh, wait, that diode.
That's different. Yeah.
Yeah.
At diode you can. Yeah. At a diode you can. Yeah. But this is another way to reduce the antenna effect. Okay. All right. I talk about this stress effect, right? Remember I talked about the stress, right? The LOD stress effect and the different transistors. Look at in FinFET. It's even worse, right? So if you don't put enough dummy, so this you see I have only one dummy on the side. You see all these transistors will see different value of the stress. If you put a lot of dummies here, you see in the middle, you have plateau. This is becoming a common practice, right? So I think I roughly mentioned this. So in the modern technology node, the dummy that you put there is not just one, not just two. You need to put a few, okay? And the right way to do this, you got to do a pre-layout. In the pre-layout, you can experiment how many dummy you want to add, right? Just keep adding until you see, oh, there's no difference. You see that? Then you say, oh, I got it. That's how many dummies I actually need. You see, any simple design like this become an extra burden, right? So you see, for you to become really expert, to be able to design FinFET, become quite valuable, very valuable. All right, so dummy is important, all right? So you probably need to understand, in the future, whatever technology that you get, you got to investigate. Of course, you cannot just get at infinite dummy, right? Then your manager will yell at you, might yell at you, right? What are you doing? That the whole chip are just dummy. Yes, you protect your device very well, but you waste all the money, right? So it's a life dilemma for the future, right? You gotta face. There are also increasing trends that people try to avoid using resistor, because right now you no longer have the very high precision resistors, so people try to use a fake resistor, right? So you can use active device, right? For example, the device in trial mode. I might have mentioned this in 530A, right? So yeah, in trial mode, transistor, sometimes we call that as a MOSFET resistor, right? Okay, so people are doing that. For example, sometimes we do want to do impedance control, they just use active device. So basically there will be less resistor. Turns out that BJT and diode, compared to planar device, it's also less ideal, in the FinFET. You have more variations, and all that. So you probably need more offset cancellation techniques, if you are dealing with this. Okay. So a lot of research, doing this no diode based circuits, it's also become popular. By the way, you're gonna see this coming all the time in the circuit community. For the same reason, I told you that in the old days, supply voltage is 5 volt, right? So people do a lot of cascode, right? So there are a lot of fancy techniques people do this, and by the way, they are very elegant. And before you know it, a few years down the road, everything disappeared. Right? All those fancy techniques to do cascode, it's all gone because power supply now becomes so low. Right? So same here, yeah. So basically, you're gonna see some techniques gonna prevail, some techniques you're gonna stop. Self-heating, is a big issue, right? Remember I talked about this channel, being so small you can trap. So you know what? People actually use VR to dissipate the heat. Can you believe that? you stack the VR like a heat sink, right? So you look at this and say, well, what are you doing? Are you building a, I don't know, mansion or skyscraper? No, I'm building a heat sink. Okay, so you can, the good thing is that you can be very creative, okay, when you get to the FinFET. The only thing just that, because we as the circuit designers, we oftentimes rely a lot on our past experience. In the past, we did not face this. How do you know about this, right? So oftentimes we learn by mistake. So you do it, doesn't work. Yeah, let's see what's going on here. Remember I talked about thermal images? People do thermal images. Also, wait, this is way too hot. What's going on? So then let's start figuring out, how to do this. Right. So you can see, people try to use the metal as a heat sink, and you can also use a substrate because silicon substrate that can also source to dissipate the heat. Okay, so basically, we are facing, the design is facing a lot of uncertainty right now, right? So basically, we just need to do more iteration. I think that's the bottom line. Maybe you have more iteration in your tape out process, right? The MPW, basically our prototyping, process. Even after the tape out, they will continue to refine the process. Okay, how they do this metal gate, how they do the metal, they will continue to refine, right? So every new technology right now, they keep respinning. Okay, so every fab, even though you say that the same node, just depends on different fab. So they have different fab, right? They have different fab. So every fab, have a new recipe. So they will say, oh yeah, you got to do this. So it could be that the TSMC fab in Arizona will be different from the TSMC fab in Taiwan, right? Because they all have all this process development, going on. So you just don't know, right? So they have all this sophisticated, process development and refinement going on. Okay, and here are a few very tricky model parameter, right? So like threshold voltage, like mobility. It's so hard to model, and they usually take a lot of spins, to actually characterize and then hopefully to give you a more accurate model, right? Like RC parasitics and things like that. Okay, yeah, I'm not sure if I can finish this because I'm almost out of time. Today is what, Monday? Friday we still have class, right? Yeah. Okay, fine. Let me save this because I think this is kind of interesting. So let me save it for a little bit more time. So I'll come back on Friday. I'll continue from here. Okay, any questions? Okay, if not, see you.